Hello class, now we're going to begin with lecture 2, which is primarily going to be about unions and intersections of sets and how to count using the addition principle. So lecture 2, adding it up. And so we'll start with the same problem I introduced in the first lecture. How many different ways can you make change for 25 cents using pennies, nickels, dimes, and quarters? And so last time I had given the answer to this problem, but I didn't say where the answer came from. This time we'll actually figure out how to answer this problem. And so suppose that you were going to make change for 25 cents. Well, first you'd ask yourself whether or not you have any quarters. So then you break the counting problem up into different cases. So first you consider the case where you have at least 1 quarter. And then the other cases are all cases where you have no quarters at all. And so after case 1, the second case would be, suppose you have no quarters, but you have at least 2 dimes. You can always make change using 2 dimes, and then you see that adds up to 20 cents, so you'd have to give change for the remaining 5 cents using nickels or pennies. Of course, you could also be in the case where you have only 1 dime and no quarters, or you can be in the case where you have no quarters or no dimes. And so what we're seeing here is that if we let A be the set of all ways to make change for 25 cents, we see that we've managed to break this set up into a bunch of subsets. And the subsets correspond to the ways that you can make change according to the rules in the corresponding case. So A1 corresponds to case 1. That's all the ways you can make change where you use that quarter, or you use 2 dimes, or you use exactly 1 dime, or you only use nickels and pennies. And the principle we're going to get at today is to point out that in this case, the way to solve this problem is using the addition principle. And in general, that's the idea behind the addition principle. It is replacing your counting problem with a bunch of independent counting problems so that your answer is just the sum of the individual answers. And whenever that happens, you hope that the individual subproblems are easier to compute. Now we define union of 2 sets. Given 2 sets A and B, the union is the set of all elements such that X is either in A or B or possibly both. And so one way to think of these is that these are 2 different bags of objects, and then the union is what happens when you pour all the objects into a common bag together. So for instance, if A is the set consisting of the numbers 1, 2, and 3, and B is the set consisting of the numbers 2, 4, and 6, then their union consists of 1, 2, and 3, because those are elements of A, and 4 and 6, because those are elements in B that are also in A. Of course, it is worth pointing out that the 2 is in both sets, so the 2 only appears once in the union, because we don't usually allow repeats in a set. Next, we also define intersection. Now, the intersection of 2 sets is the elements that are in both sets. So X has to be an element of A, and X has to be an element of B. So for instance, using our 2 sets from above, the only elements they have in common is the element 2, and so the intersection is the set containing only 2. It doesn't have 1 because 1 is in A but not in B. Likewise, it doesn't have 6 because that element of B is not in A. It only has the elements they have in common. You usually see intersection of sets in real life whenever you're actually talking to someone and you're looking for things you both have in common. You're looking for things that lie in the intersection. Whereas a union would be you're looking for things that at least one of you like, possibly both. So of course it's worth emphasizing that the intersection is always a subset of the union, because anything that lies in both sets has to lie in at least one of the two sets. Thus, we arrive at our first addition principle. If you can write a set as the union of two sets, such that those two sets have nothing in common, then the number of elements in the original set is the sum of the number of elements in the individual sets. In other words, if you can partition some set into two groups, such that no group has a member in common, then the total number of students is the sum of the number of students in each group. It is worth noting that this addition principle doesn't really apply to our original problem the way I'd stated it, because our original problem had 4 sets, not 2, but we'll get to that in a little bit. First, we'll actually describe an application that uses the additional principle as written. Alright, so let's consider the following pizza problem. We have a pizza and we want to put toppings on it. Furthermore, let's suppose that your favorite pizza joint is having a sale on 2 topping large pizzas for $5, and that this is the list of toppings they have. And so you want to pick 2 different toppings for your pizza. And let's consider the ways that we can solve this problem. First off, let's suppose that you decided that you are one of those weird people who actually likes anchovies, and you decide to put that on a pizza. Well, we'll call that set A. It's the set of pizzas where the anchovy is on the pizza. And of course, we can let N for normal be the set of pizzas where the anchovies are not on the pizza. Then we see that the total number of options for solving this problem is the union of these 2 sets, because either you have an anchovy or you don't. And furthermore, these 2 sets are entirely disjoint. Of course, I'm skipping over some details. By pizzas, I'm specifically assuming that they're only 2 topping pizzas. Then by the addition principle, we see that the number of possible pizzas has to be equal to the number of pizzas that have anchovies on them, plus the number of pizzas that don't. And so then we consider how to solve this problem further. Now, if we're in the case where we have anchovies, then we've chosen that particular topping, and then we see that there are exactly 7 more toppings left. It's worth pointing out that the order of toppings doesn't actually matter on a pizza. So this is an example of unordered counting problem. And so there are 7 possible choices left, and so there are 7 possible pizzas that have exactly 2 toppings that include anchovies as a topping. Now, of course, we admit the truth that anchovies are really gross, so let's consider the case where we don't have anchovies on the pizza. Well, then we have 7 more toppings left to pick from, and we have to pick 2 of those toppings. And so we still have a lot of work left, but we've now narrowed our problem down to solving n, the size of n. And as we will see soon, that is an example of something called a binomial coefficient, which will be introduced later in this lecture, but you can actually solve this problem the rest of the way. 7 choose 2 is the number of ways to pick 2 things out of an unordered collection of 7 things. And so there actually is a way to solve this problem the rest of the way. And so, as illustrated, here is one of the possible solutions. This is the solution where you decide to put pepperonis in pineapple, because clearly we all know pineapple belongs on a pizza. And so that's just one of the many options. And so hopefully I haven't ruined pizza for life for you. Now we will discuss unions and intersections in general. So given some set I, which we call the index set, and for each element of the index set, another set AI, The indexed union is the set of all elements that appear in at least one of the sets AI. And the set indexed intersection is the set of all elements that appear in every single last set AI for every I. So for example, suppose that I is the set of natural numbers, and define AI to be the set of all natural numbers d, such that d is a factor of I. So for instance, we would see that A sub 6 is a set containing 1, 2, 3, and 6, because 1, 2, 3, and 6 are all factors of 6. And in this case, we see that the set indexed union is nothing more than the natural numbers itself, because every number is a factor of some other number. In particular, it's not hard to note that every number is a factor of itself, which kind of forces the union to be the whole set. On the other hand, the intersection is only the element 1, because 1 is a factor of every number, but it's the only number that's a factor of every number. As a second example, you could consider letting I be the set of students in this class. And then for each student, we could let AI be the set of classes they're registered for. And in that case, the union would be the set of classes that at least one student is taking, which is obviously going to be a very, very big set, which I can't describe. On the other hand, the intersection would be the set of all classes that every student is registered for. And based on looking at some student records, it's quite clear that this class is it. This class is the only class that every student is registered for. Of course, the reason why I'm introducing the concept of union is for arbitrary sets is because usually for us, I is going to be a finite set, and the idea is given some sort of counting problem, you want to rewrite it as a union of other smaller sets, so that then you could try to count each of the smaller sets separately. However, of course, there are some counting problems when you try this, as we'll see when we look at the addition principle in a moment. Now we discuss the generalized addition principle. Given a set X, if you can write it as a union of a bunch of subsets AI, where I is running over some sort of index set, that's finite. It's worth noting all these sets have to be finite. And for any pair of indices, I and j, that are not the same, that the pairwise intersection of those two sets is non-empty, then the number of elements in X is just the summation of the number of elements in each of the subsets. And if you're not comfortable writing summation notation this way, for right now it's worth pointing out that if your index set is just the set of numbers 1 through n, what you're really saying is that the number of elements in X is the number of elements in the first set, plus the number of elements in the second set, on, all the way up to the number of elements in the nth set. And so one way I get used to thinking about this is I've got some sort of big set, and I've chopped it up into a bunch of smaller pieces, A1 through A5, and so the number of elements in the box is the number of elements in each of the pieces, or well, the sum of the number of elements in each of the pieces. It's worth pointing out for later in this course, if you actually take the set containing each of the subsets as their own element, this is called a set partition. And so a set partition is a way of decomposing a set into a bunch of smaller subsets, such that each element appears in exactly one subset. So for example, the set whose elements are sets containing 1, 2, and a set containing 3, 4, forms a set partition of the set of numbers 1 through 4. Is a set partition of 1 through 4, because every number appears in exactly one part exactly once. So now we return back to the original problem we started with at the very beginning of the lecture, making change for 25 cents. In this case, I've changed the notation up a little bit. Q is the set of all ways to make change for 25 cents where you use at least 1/4. T is the set of all ways to solve that problem where you use exactly 2 dimes. D is the number of ways to solve that problem where you use exactly 1 dime. And N is the number of ways to solve the problem where you use only nickels and pennies. And we see that, as we saw at the beginning of lecture, the answer to our problem, the set of answers to our problem is actually the union of each of these sets. And the sets are disjoint, and so by the addition principle 2, we could solve the problem this way. And so then it suffices to solve each of these individual subproblems. There's actually only one way to make change for for 25 cents using a quarter, namely the quarter itself. It turns out there are exactly 2 ways to solve the problem using 2 dimes. You either use 5 pennies or a nickel. Similarly, if you're only allowed to use exactly 1 dime, then you can only use nickels and pennies for what's left. And so either you have to use 3 nickels for the remaining 15 cents, 2 nickels and 5 pennies, 1 nickel and 10 pennies, or 15 pennies. And that's 4 different options, so the size of that set is 4. Finally, if you're only going to use nickels and pennies, well then you can use at most 5 nickels, or 4 nickels and 5 pennies, or so on and so forth. I leave it to you to check that there are actually 6 possible ways to finish that problem. So we get the answer we had in the previous lecture, that the answer is exactly 13. Admittedly, this seems like a lot of talking for such a simple problem, but the whole point is that this principle of breaking a problem up into a bunch of disjoint subproblems and solving them each separately is very useful in mathematics, and we'll see it come up again and again throughout the semester. And so it's easier to explain it using a simple problem rather than complicated problems. Now we discussed the concept of binomial coefficients. So we're going to go a little bit beyond the book here. Given a finite set x and an integer k, positive integer, we define x choose k to be the set of all subsets of x that have exactly k elements. So for example, if I consider the set consisting of ABC, then ABC choose 2 is the collection of all subsets of ABC of size exactly 2, and so either you have A and B, A and C, or B and C. Each of these sets is a set of size 2, and that's all the possible subsets of size 2. And so this is the binomial collection of size 2, the set of all 2 sets of ABC. And one place where we've already seen this set before is in the pizza problem. If you look at the pizza problem as studying all 2 subsets of the set of all possible toppings we have, then you're just looking at the number of 2 subsets of the toppings. It is worth noting that the number of 2 subsets does not actually depend on what we named the toppings, but in fact we actually would get the same answer if we replaced t with any set of size 8, because for reasons that we'll get into in a later lecture, and so the binomial coefficient can be defined to be the number of subsets of size k of a set consisting of the integers 1 through n. And you can replace that with any subset of size n and you will get the same answer, and this is the definition of the binomial coefficient. That's the binomial coefficient. So now we'll see how to use the addition principle to study binomial coefficients. So given an integer n and a positive integer k, it turns out you can decompose the set of k subsets of the integers 1 through n into two disjoint subsets. The first subset consists of all k subsets of the integers 1 to n minus 1, so these are the subsets that do not have the element n in them. And the second set consists of all the subsets of size k where n is an element of the subset. To make this completely explicit, let's let n be 4 and k be 2. We see that we can decompose the collection of two subsets of the integers 1 through 4 into two collections. The first collection are the subsets that don't have the number 4 in them, and the second collection are the subsets that do. That's exactly what this is doing, and so that tells you that we can write n choose k as n minus 1 choose k plus whatever the size of this second set is. And the answer in that case is going to turn out to be n minus 1 choose k minus 1, because given a set S that contains the element n, you can always consider intersecting that set with the numbers 1 through n minus 1 instead. And it turns out if you do that, the size of this new set is 1 less. It's size k minus 1. And it turns out that this is what they call a bijection, which we haven't discussed yet. You can reverse the operation. And so any subset of size k that contains a given element can also be viewed as a subset of size k minus 1 that doesn't have that element. And so you actually do have this Pascal's relation modulo some base cases, namely n choose 0, the number of 0 subsets is always going to be defined to be 1. And likewise, that's the set of all n subsets. And of course, we're going to define n choose k to be 0 if k is bigger than n. If k is much, much bigger than n, there are no k subsets. And so that's it for this lecture. In the next lecture, we'll talk about binomial coefficients more in depth. But I wanted to include that on this lecture because it actually uses the addition principle right here in order to finish the job.